Today, we're diving into a major leap in quantum computing, the simulation of a massive protein structure. This isn't just a small step, it's a huge jump in scale.
The title says it all. A team from Cleveland Clinic, Riken, and IBM has simulated a protein with over 12,000 atoms, which is a significant milestone. The achievement here is simulating the electronic structure of a 12,635 atom protein-ligand complex. That's a huge system to model at the quantum level.
Wow, 12,000 atoms? What does electronic structure mean in this context, and why is that such a big deal for a system this size?
It means understanding how electrons behave within the molecule, which dictates its chemical properties. This represents a 40-fold increase in system size compared to their previous work just 4 months prior.
A 40-fold increase in size in just 4 months is incredibly fast. That suggests a rapid pace of development in this area.
This work relies on what they call quantum-centric supercomputing, QCSC, calculations. It's not just quantum computers working in isolation.
So, quantum-centric supercomputing is a key term here. Does that imply a blend of classical and quantum resources?
Exactly. The quantum part involved 2 IBM Heron R2 processors, each with 156 qubits, using up to 94 qubits for sampling. That's a significant quantum resource.
And the other half of quantum-centric supercomputing, then, must be the classical side. What kind of classical horsepower are we talking about?
The classical heavy lifting ran on Riken's Fugaku and the University of Tokyo's Miyabi-G supercomputers. These are some of the world's most powerful machines.
It sounds like they're throwing serious computational power from both paradigms at this problem. This is truly a hybrid approach.
Given all that power, I'm curious if this new method outperforms existing classical methods for protein chemistry yet.
The paper is quite clear. It states, it does not yet outperform the best purely classical methods for protein chemistry.
That's an honest assessment.
However, the crucial point is the trajectory of improvement. Going from 303 atoms to over 12,000 in just 4 months is incredibly fast.
That's a key distinction. It's not about immediate supremacy, but the rate of progress. It's the potential for future breakthroughs that's striking.
The authors predict that quantum-centric approaches to computational chemistry could become competitive with classical alternatives within the next few years if this pace continues.
That's a powerful statement. It suggests that while not a winner yet, it's a rapidly closing gap, making it a technology to watch very closely.
So how did they achieve this rapid scaling? The paper details a novel workflow that combines quantum and classical techniques strategically.
Let's dive into that workflow. How did they actually manage to simulate such a large and complex system?
The core technique is Sample-based Quantum Diagonalization, SQD. This is a method IBM has been developing as a flagship application for its QCSC architecture.
SQD, okay. So how does this method divide the labor between the quantum and classical parts of the supercomputer?
With SQD, the quantum processor generates samples representing electronic configurations, specifically Slater determinants. These samples are the quantum contribution.
So the quantum computer is sampling potential electron arrangements. What happens to those samples next?
Then, classical supercomputers then take those samples through configuration recovery, subsampling, and subspace diagonalization to estimate ground state energies. The classical machines do the heavy post-processing.
It's like the quantum machine provides the raw, difficult-to-get data, and the classical machine makes sense of it. That's a clever division of labor.
Beyond SQD, What makes this approach truly scalable is wave function-based embedding, or EWF. This is how they handle the sheer size of the protein.
Embedding? Does that mean they're breaking down the large molecule into smaller, more manageable pieces?
Precisely. EWF fragments the protein into computationally manageable clusters. The classical methods handle the simpler clusters, which is efficient.
And the quantum part? Is that where the hardest calculations go?
Yes, the quantum processor, using SQD, tackles the clusters where electron correlation is strongest, where classical methods struggle most with accuracy.
This hybrid strategy makes so much sense. Use the quantum computer for the parts it excels at, and classical for everything else. What was the critical algorithmic advance for scaling?
The critical algorithmic advance was applying linear scaling methods to the MP2 step for fragmentation. Without this, the cost would have been astronomical.
So it wasn't just bigger hardware, it was smarter algorithms. It mentions the naive approach would be 24 million times more costly.
Their insight was that electron entanglement is localized in large proteins. Quantum mechanical correlations beyond about 7 to 10 angstroms are negligible.
That's brilliant. By exploiting a physical property of large molecules, they could collapse the computational scaling from exponential to effectively linear.
This EWF plus SQD is a genuinely modular design. As quantum hardware improves, they can tackle harder fragments without redesigning the whole workflow.
That's a powerful point. This isn't a one-off hack. It's an architecture that can evolve with the underlying technology.
This scale of classical resources and the integration demonstrate that the engineering infrastructure for production-scale quantum chemistry workflows is being actively built, not just theorized.
This shows a maturity in the field we haven't seen before, moving beyond individual experiments to integrated large-scale systems.
This hybrid approach and its scaling directly impacts fields like drug discovery, opening doors to previously intractable problems.
So how might this advancement in simulating molecular interactions specifically change the landscape of drug discovery and other applications?
This second article directly connects our previous discussion to practical applications, noting how quantum computers accelerate molecular analysis.
That's exactly what I was thinking. This massive protein simulation has clear implications for drug development. How does it enhance drug discovery?
The article suggests this could be potentially revolutionizing drug discovery. Understanding molecular interactions is central to finding new medicines.
The conventional methods are often complex and time-consuming, so any acceleration here would be a huge win.
Quantum computers are being used to simulate and model molecular interactions with greater speed and precision. This directly addresses those bottlenecks.
More precision means a better understanding of how a drug will actually interact with a target protein in the body, right?
It provides deeper insights into how molecules behave, interact, and react, which is absolutely crucial for designing effective drugs from scratch.
So instead of just trial and error in the lab, you can simulate many more options virtually to narrow down the best candidates.
Precisely. This enhanced computational power enables scientists to explore a wider range of potential drug candidates and predict their efficacy.
That's fascinating. It lets researchers cast a much wider net and test more ideas in simulation before moving to expensive and slow experiments.
Ultimately, this could significantly shorten the drug discovery timeline and reduce the costs associated with traditional research methods, which is a massive economic and human benefit.
The ripple effects are huge. Faster and cheaper drug discovery means new treatments reach patients sooner and potentially at a lower cost.
Consider the current simulation of a 12,635 atom protein. This level of detail could allow for extremely precise modeling of drug binding pockets.
So you could predict exactly how a drug molecule would fit and interact with a specific target, even in a very complex protein environment.
This moves beyond just understanding chemistry to directly impacting how we develop new therapies for a wide range of diseases.
It feels like we're watching the early stages of a fundamental shift in how pharmaceutical research will be conducted.
This record-breaking simulation, enabled by quantum-centric supercomputing, truly illustrates the growing power of hybrid approaches in scientific discovery.
It's not just about what quantum computers can do alone, but what they can achieve in partnership with classical systems. That's our big takeaway today.
I'm Maya. Thanks for spending this with us.
I'm Arjun. The next walkthrough is in 3 hours. See you then.